Hey, PreCalc, we are going to try and get through some exponential modeling here. I'm just going to grab my highlighter because almost everything is filled in for you here. We know growth is when b is greater than 1. We know decay is when b is less than 1. Obviously, it's still going to be a positive number because that doesn't happen. We added in some things about the a value. We know basically that it's going to be for a growth, it's going to increase over its domain left to right. And that is, of course, as long as the a value is positive, right? And that just means that we don't have a reflection of some sort. So without a reflection, we know that a growth increases and a decay decreases. All right, we have a lot of applications. Hopefully you will run into those in your science world as well. So we can get these things to be the same. But here's what we're working with. We have an initial value, initial population. Okay, so this is essentially A. And then we're going to come up with a b value, and we're going to take that to some time value. Now, what we do here is we say that if it's a growth, then we're going to add that on. If it's decay, we subtract it away, or we take that r value, and then we translate that to being a negative if it's a decay, and that's how we deal with those. So that's what all that wordage is just talking about. So if we take a look at the first couple here, for each of the following, does the function model growth, decay, find the constant? Okay, so here's what we have. And what's happening is it's greater than 1, so we know it is a growth. And then what I like to do to make this super simple is to take out the 1, because that means that it stays the same. And then for the rest of it, I have 0.075. And what I have to do is change that out. So in some texts, they might say, okay, 0.075 is going to be our growth factor. But if they want it as a percent, remember I have to move 2 places. So 7.5% growth looks like 1.075. Okay, so that's kind of the translation. So we're always dealing with working around 1. So when it's a growth, it's how much more than 1. And when it's a decay, like the next one here, we know that this is less than 1, so it's going to be a decay. Remember, I don't care about the a value, the b value. So my 0.084. All right, now this is going to tell me what's left. Okay, so this one works a little bit backwards. So what we're going to do is we'd have 1 minus 0.084. All right, so we're actually looking at, right, so let me write that out for you. 1 minus 0.084. So that means we're looking at 0.916. But that's not my percentage yet. Let's move it over. So this is a decay of 91.6%. And that's how we're going to get our growth versus decay. Yeah, let's make that a little bit easier. These numbers were a little bit tough, I'll be honest. If you don't remember this from Algebra 2, you're like, what is he talking about? Okay, so exponential function with initial value of 12. So 12, y equals, we can use f of x, increasing at a rate of 8%. So 1, because it's an increase, 1 plus 8%, 0.8, and that's going to be over some sort of time factor, whether it's hours, days, whatever it is. So hopefully that makes that a little bit easier. Exponential function, initial value, 500. Okay, decreasing. So I know it has to be point, right? It cannot be more than 1. Decreasing at 85 or 15%. Okay, so that means that we're going to deal with 1 minus 0.15. You know what? Why are we doing that? Let's talk about it as percents. What's 100 minus 15? That's 85. What's that as a decimal? 0.85 to the exponent. So the point being, I want my equations, and you do too, to always represent what is left, not what I lost. Okay, so when we look at a decrease or decay factor, we're going to say, okay, I had 15% taken off of my test. What grade did I get? And then turn that back into the decimal. I think I talked about this way too much. But hopefully it makes sense. If not, you know what? We're going to deal with it in class. All right, so exponential growth. All right, so some things that we know, if it's constant, that means it grows 0. All right, well, that makes sense, right? Because we would have just a 1 in there, or we'd take it to the 0 power, anything like that. All right, if population increased by half, right, so we would use 1.5. Okay? If population doubles twice the original amount, that means it increases 100%, so that means the b value would equal 2 because we're talking about how much more than 1. All right, so those are all some like basics, just getting the idea, right? How much more than 1 Then we have this little tricky part, because what I want to throw out here to you is we want to try and keep things basic. So if things are going to, if something is supposed to double, right, that's 2 as a base. So it's time over the um, number of days, hours, whatever it is, to double. So whatever it's in. We're going to model this here just in a second. Okay. But if we're dealing with, we want some value, and we're going to deal with half-life. Now we're going to deal with this in 2 different ways in this chapter, but this time it's the time that it takes to be in half, right? So this is the time that it takes to double. This is the time that it takes to fall, to decay into half of it. All right, so I'm going to model that in the next couple problems, but I just want to set the stage with it for you. So this one, we just want to write an equation. I can do that, y equals or f of x, whatever we want to use. Population, initial population, so that's a is 9. It's going to double, so 2, and it doubles every 3 days. All right, so this is t over 3 because it doubles in 3 days. So then we could find out, okay, we want to model that growth. So whatever time frame they give us after that, then that's what we plug in for t, or we could solve for it. And we're going to get to that today as well. All right, so very similar. We're going to deal with this. So we have half-life. So y equals, we're going to certain substance, 20 days, 5 grams initially. Okay, 5 grams, 5. Half-life, so 1/2. Okay, and I'm thinking about the time that it takes to be half of it. Okay, so the time that it takes for half of it. So that's the time is 20 days. Time divided by 20, because it takes 20 days to end up with half of it. Okay, so let's try and get this to make sense, because you're like, okay, I'll follow along and just try and trust you on this one. Okay, think about this. If we started off with 5 grams of whatever it is, if I put 20 in here, right, so here we go, 20 divided by 20 is 1. So I would take half of the 5, right? So that lays out the stage for half-life of a substance or whatever it is. Okay, so that's always going to be the time it takes for half of it, the time it takes to double. So that's why we used D up here to double and H up here to half. Okay, so that's the first set, and that's what we're going to model our problems on as we move forward. But then we have basically continuous growth. Okay, so these are implied that we're definitely going to grow the whole time and work through those. So this one, the work has already been done for us to find out its growth rate. It looks a little bit different because we're in a different formula. Okay, again, all things that we'll deal with throughout the chapter. T is in hours. Okay, when will the bacteria count past 1,000? So I want to know when this is going to be equal to 1,000. Okay, so 1,000 equals 50. E, remember that's a number, 0.439 T. All right, now let's pause here for a second. All right, we're okay. We've plugged in 1,000. Right, now, what this book says to do is, okay, take each side, make it y equals, and find the intersection. This is crazy because you guys have already been through Algebra 2, so you know exactly how we're going to solve this. So we're going to get a little bit ahead of ourselves in this chapter, but we're going to use some things that you guys totally know. Okay, so 1,000 divided by 50, there are 20 of those, 0.439 T. Now, I'm not the best writer, but I intentionally left some space in here because this is e to that power. All right, now what I'm going to do is I'm going to introduce one more thing because my variable is in the exponent. You see it up here? So I'm going to introduce the natural log to both sides because the natural log of e is 1, and this exponent is going to come down but stay on this side of the equal sign. So here's what I have. I have the natural log of 20 equals 0.439 t. Right? So if you remember that from Algebra 2, we're going to start using it. If you don't remember that from Algebra 2, we're going to start using it. Okay, so I'm going to find on my calculator the natural log of 20. Now it says here that it's about 2.99573 equals 0.439 t. Then I just want to divide that number by that 0.439. Okay, 439. All right, so let's do divided by 0.439, and voila, we find out that the time it takes is 6.824. 4. I rounded that off a little bit. Now let's check here. The time is in hours. Now, if this were a fancy-dancy standardized test, we might say, okay, well, that's 6 hours, and how many minutes is that if you have 0.824 of an hour? I'm not going to get there because we get a lot of stuff going on here, okay? So recap, ready? If we're going to double it, get a 2 in here, how much time does it take to double? If I'm going to do half-life, right? So we're going to do 1/2 is our base, right? And how much time does it take to end up being half of what it started with? All right, so that's a quick recap. We're going to dive into all this stuff in class. And remember, you can use the natural log here or regular log functions. I would prefer we not have to do this because that's a pain, but it can be done. If you get stuck on something, remember, if you have any equation that you need to solve, you have one unknown, you can set both sides equal to each other, find the point of intersection on the graph. Okay, this is not this problem. Disclaimer. Peace.